Good evening all, and welcome to tonight's TI Technology webinar hosted by Texas Instruments Australia. We are really excited to bring you Exam Readiness Specialist Mathematics with Chris Erison and Raymond Rosen. My name is John Bayman. I am your host for this event. I teach mathematics to years 7 to 12 students at Lachlan Catholic College, Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. And I'm excited this evening to introduce our first panelist, Mr. Chris Erison. Good evening, Chris.
Good evening.
Chris Erison has been teaching mathematics for over 25 years, teaching all aspects of the VCE mathematics course. At Melbourne High School, he is responsible for implementing CAS technology and developing materials to assist teachers and students to get the most from their TI-Nspire CAS calculator. Chris, thank you very much for joining us this evening.
Good evening, everyone.
Our second panelist for this evening is Mr. Raymond Rosen. Good evening, Ray.
Hello, how is everyone?
Let's hope they're well and excited about hearing what you have to say, Ray. So as you can see, Raymond is a guru on all aspects of the VCE mathematical methods and specialist mathematics courses. He shares this knowledge in writing textbooks and presenting at national and international conferences, as well as joining us this evening. So, Ray, thank you very much for joining us. So, with no further ado, Ray, I will pass over to you, and I'll allow you to share your screen and your knowledge of the VCE Specialist Mathematics course.
Okay, so you should be seeing my screen at the moment. What I'm going to do, our first little example will be about a cycloid question. So this is a typical sort of analysis type question in Specialist Maths Exam 2. So a ball rolls along a curve and moves so that its position vector is given by the parametric equations x equals t minus sine t and y equals 1 minus cos t for t between 0 and 2 pi. The path of this curve is actually called a cycloid. What we want to do is we want to find a lot of parts to this question. We want to find the gradient of the curve at any point t. We want to find the coordinates of the curve where the gradient is parallel to the x-axis. We want to sketch the path of the particle. We want to find the speed at any time t, the length of the curve. Now the arc length is a new topic which has been introduced to specialist maths. The total area bounded by the curve and the x-axis, and if that area is rotated 360 degrees around the x-axis, we want to find the volume that's formed. Now, all of this question will be done on a notes page, which is an interactive document. So although we're actually doing it for this particular curve, changing the values of x and y, the whole thing will recalculate for any other equation or any other curve. Alright, so pressing the on key, we'll add a notes page to this document. The notes page is the yellow icon second from the left there. And in a notes page, we actually can type in text or copy stuff from a Word document and cut and paste things. But if we're going to do any mathematics within a notes page, we have to press it in what's called a maths box. So if I just press menu now, you'll see that things are a little bit different, and we have to insert a maths box. So any maths box is inserted with Control M. So if we know Control M, we can do that at any time. So what I want to do here is define the functions. So things now get a little bit, we've got to go to the calculation menu, and then we get our familiar menu that we've had before. So define, if I define x1 of t equal to t minus sine t. Now I can type sine t, or I can get it from the trig menu as well. Another maths box is actually opened, so I can actually just type in define y1 of t to be equal to 1 minus cos of t. Now they're done. We want to have the starting value here, which is sort of between 0 and 2 pi, so I'm going to define a variable a to equal 0 and a value of b to equal 2 pi. Now, another little nice shortcut, although we've got a pi button down the bottom here, we can actually just type in the letters pi and it knows what pi is. Okay, so that's basically set up the problem. Once we've done that, as I said, everything else can actually be calculated from there on end. So what is the gradient? The gradient is dy dx, which, according to the chain rule, is dy dt dt dx, or if you like, the gradient dy dx, so I'll define m of t to equal, it's going to be dy dx divided by dx dt, So we can get these from a template. So the numerator is going to be the derivative of the y. So once again, I'll get this from the template next to the book command, or I could get it from the calculus menu as well. So I want d by dt, so I've got to type a t there. And now here I could press the var command to bring up the y1. They're my variables that are defined. I must type in the t, move the cursor to the denominator here, and in a similar way, just use the same template, d by dt of x1 of t. I know what it's called, so I'll type it in. So that gives me the gradient function at any particular value of t. We don't actually see it. The maths box just says it's done. But if I just type in m of t, then it tells me that it's 1 over tan of half t. All right, so to find the coordinates on the curve where the gradient is equal to 0, we basically want to solve where the gradient is 0. So once again, we can use the menu algebra command, or once again, we're in a maths box, so let's just type in solve. I want to solve where m of t is equal to 0 for t. Now, I won't press enter yet because when I solve a trig equation, we often have general solutions appearing. So I only really want to find the particular value of t between 0 and 2 pi, or between a and b. So I'll use the given command here. So control equals, and let's choose, I call this the given or the pipe command, and I'll issue that between a less than or equal to t less than or equal to b. So that way I won't get multiple solutions or general solutions, I'll only get the one value. So the value t equals pi is the coordinate, well it's not the coordinate, it's the value of t, where the gradient is parallel to the x-axis or the turning point. All right, now let me define another function here. Let me define r of t to be equal to a vector. And once again, we can get the vector template from the template next to the little book command or the catalog command. And the one I want this time is this two-dimensional vector. It's a vector, it's really a matrix. It's a 1 by 2 matrix. So in the first template here, I'm going to type in x1 of t. Alternatively, I can get it from the menu, or tab across now to the second little box and type in y1 of t. So that gives me basically the position vector. Now, if we're going to be using this in the exam, of course, students should be writing with i's and j's, but the I component is the x1 of t, and the j component is the y1 of t. Well, knowing the t equals pi is the value, if I just go r of pi, once again, being a bit lazy, I'll type in pi rather than getting it. So the x value of the coordinate of the turning point is x equals pi, and the y value of the turning point is 2. So defining this function is very, very nice because we can also now sketch the graph of this function. So it is a parametric function, so if I press the on command and go to a graphs page, we went to a calculator page, let's go to a graphs page, and now we're on a graphs page, press the menu command, and graph entry edit, parametric is the one we want to get to now. Now, pressing up arrow, because they're already defined for me on the notes page, the calculator page knows all about them. So once again, I could have changed this step value here from 2 pi, although that's okay, we'll leave it as 2 pi. No, perhaps we should, yeah, no, it's 2 pi is fine, we'll leave it as 2 pi. So when I press enter, the graph will appear. And we'll just change the window settings so that we get a nicer little picture. Some typical sort of settings here. I think I'll choose what x equals, say, -3 here, just to make a nice viewing window. And the x maximum, we'll say 8. X scale, I'll say 2. The y minimum, I'll say -2. The y maximum, I'll change to say 6. And we'll set a scale of 2 there. So then we get a nice graph, and we can see that the turning point, or the maximum value, is the point where x is pi and y is 2. So that gave me the turning point there of that graph. All right, so let's come back to our notes page now and work out the rest of the properties that we're after here. We're also after the velocity. Now, the velocity is the derivative of the displacement. So I can define v of t to be equal to the derivative of the position vector. Now, this is going to do both of them. It's going to differentiate d by dx of t and y of t as well. So this is the derivative of the position vector, the velocity vector. So once again, it just said done. So if I want to see what the velocity vector is, let's just see what the velocity vector is. So it's 1 minus cos t and sin t. Now, as I said before, the advantage of doing this on a notes page is that really all I have to do here is to change x1 and y1, and all of these other functions down the bottom here will all automatically update as well. So the final parts for this sort of question were after the arc length. Now, the arc length is just the integral of the speed. So the speed is the magnitude of the velocity. So let me define, once again in a maths box, I'll define the speed at any time t to equal the magnitude of the velocity vector. Now, to find the magnitude of a vector, we can use what's called the norm command. So if we go menu, calculations, matrices and vectors, then we can find the norm. Norm, N-O-R-M, is the magnitude of the velocity vector. So if I just type in v of t here, we've got the speed. So once again, we don't see what it is. The speed at any time t is a scalar given by that function there. Often you might want to use t-expand or t-collect to sometimes simplify these components of the speed. All right, so moving on with this question, the length. Now, length, I'll, again in a maths box, L-E-N-G-T-H, I'll say the length is the integral. So it's the integral, we'll get that from the template, and it's the integral between A and B of the norm of V of t. So I'll just type that in, norm of V of t. And that's the integral with respect to t. So that gives me the length. So the length is 8 units of that curve from A to B. So very nice little ideas here to actually find the arc length. Again, just stating that that's a new topic. Now, as I said, that if you were to change x1 and y1 up here and A and B, that will then calculate the arc length for any particular curve that we define as x1 and y1. All right, what about the area then? Well, the area is also a definite integral. The area is the definite integral of y dx between A and B. Although we've got to use t here, so it's y dx. Okay, I can make that y dx dt dt. Y is actually y1 of t times dx dt. So again, we'll get that from the template. This template is very useful. D by dt of x1 of t. And once again, that's the integral with respect to t there. So that's the area, y dx. All right, finally, what about the volume? Okay, the volume is assigned equal to, well, first of all, for the volume, it's pi. I'll get it from the pi button, times the definite integral. So we need the integral sign from A to B of y squared. Okay, so I'm going to put y1 of t in a bracket and then square that and then multiply that times dx dt and integrate with respect to t. So we need that template again, d by dt of x1 of t, and integrate that with respect to t. Okay, what happened there? Pi of the y squared, I don't think is quite right. D by dt, okay. D by dt there should be correct. That's correct. The area, sorry, the volume then is 5 pi squared. All right, so that gives me the area, the volume, the arc length, as I stated, for any particular curve. Now, also one of the new features of TI-Nspire that you can actually graph relational functions. You can graph things like x equals or less thans or greater thans or implicit equation curves. Now, for this particular curve, it's not possible to get y in terms of x, but in fact it is possible to get x in terms of y, because x can be expressed in terms of t. Cos t is what, 1 minus y, so t is the inverse cos of that. So what I'm going to do now is define a relation. So this is one of the new features of TI-Nspire. If I'm going to do that, I must be in the maths box. So define rel1. Rel1 is the relation of x comma y. And this is equal to x. If you rearrange this, you'll get rcos. So let's go to trig. Now this only works for this particular example, obviously. It's the rcos of 1 minus y minus, what is the sign value then? It's going to be the square root. So it's a little bit of algebra to get this one. It's the square root of y times 2 minus y. Now, the nice thing defining rel1 as a function of two variables, we can actually differentiate it using implicit differentiation. So if I go menu, calculations, this time I'll go to the calculus menu and find implicit differentiation. So implicit differentiation of rel1. Now rel1 is the relational function, it's not a function, it's a relation, in this case it is. So all my variables are then stored under the var command. So if I go rel1 and type in x comma y and then differentiate that implicitly with respect to x and then y, it gives me the gradient function there. Okay, so what happened here? Rel1 was done. Rel1 x comma y comma x comma y. That should have worked. All right, now we'll come back to that in a minute, but let me show you exactly what is happening here on the cycloid. So let me just, there it is, implicit differentiation, rel1 x comma y comma x comma y. Or you can differentiate that function as well. Notice that they're upside down because the implicit differentiation is dy dx. That one was defined there. Okay, so I think we had two equal signs there rather than x equals and x equals there. So when I go to a graph page
all very well there at the moment, Ray.
What? Sorry?
I said you're spotting all these fantastically. It's I think because it's so clear and the template's so big that when you like I said, it's obvious when there's been a slight error and students can see quite easily that it's not quite right. And then because the format's so good, you can quite easily check back. So fantastic.
Yeah. All right. Now what I've done here is I'm showing you what are the properties of the cycloid. So this is a nice little feature here. So there's the plot of the relation or the parametric graph. They're both the same graph. And what I can actually do is I can actually turn off the graph or not turn off the graph and show the graph. Now, these are nice little features that you can add to some of your documents. All I've done here is created a slider, which I've called yes, no, which if you want to look at the properties of the slider or the settings, it only has the value 0 or 1, and it's got a maximum of 1 and a step size of 1. So it can only have the value of 0 or 1. So when I change that slider, it obviously only just changes the value to 1 or 0. Now, when I've got a curve here, if I want to show or hide the curve, I can do a right-click or a control menu on that curve, and one of the little features down the bottom here is conditions. So the condition to show that curve is to show the curve when yes, no is equal to 1. So when yes, no is equal to 1, we'll see the curve. When yes, no is equal to 0, we won't see the curve. Now, the curve has got its line colour. Down here, if we click this little box for colours, it says that 7 is the colour that we're going to see. So the colour of 7 is the red curve that we'll see. So we see yes, no, we only see the curve when it's equal to yes. So I think one of the advantages of this is that we can do a geometry trace of this point as it moves along the curve. So let me just show you how we do this. If we go Menu, Trace, Geometry Trace, and click on that point. I'll explain how we got that point in a moment, and then animate that curve. We see that the point is dotted out. So we're seeing that point move along the curve. So when I click the yes-no button, we see that that point is actually moving along the curve. All right, now, how did I create that point to move along the curve? Well, I'll show you a little secret on how we do that one. We'll come back to the other graph that I created earlier and show you how to do that. So what I'm going to do is to click a point, put a point. So if we go Menu, Geometry, Point. Now, don't put the point on the graph. That's what you'd think you'd do. You'd think you'd put the point on the graph, but you don't. Put a point somewhere else. Notice in the left-hand corner the point is still activated, so I'll press the Escape key to move that one. And then I want to have coordinates and equations displayed for that point, which I'll move out the way. All right, now what I'm going to do, let's come back to the notes page here. Okay, if I come back to the notes page here, what I'm going to do is I'm going to define xc to equal x1 of some other variable which I'll call pt. Now, pt doesn't actually have a value as yet, and again I'll do another one. yc is assigned equal to y1 of pt. Now, yc and xc don't have values, but when I come back to my graph here, what I'm going to do is I'm going to insert a slider. So Menu, Actions, Insert a Slider. So I'll insert a slider. The slider will be called PT. Its value, look, I'll just say it's 0.2. Its minimum value is 0. Its maximum value is 2 pi. It would be nice if we could actually use the variables that we've got from the notes page here, but unfortunately they're not remembered. And the step size, look, we'll just say it's 0.2. Now, sometimes when we do this, things happen that it's not actually in the exact value. So rather than using 2 pi, let me just use a step size of 0.2. We could minimize the setting as well, or move it out of the way and make it look a bit prettier, but we'll just leave it for the time being. Now, this point here, what I'm going to do is I'm going to store this to the point. So right-click again, do a control menu, and variables, let's link that point to xc. Let me do the same thing for the y. Variables, link to yc. Now we'll see that that point moves on the curve as I move this slider here. And once again, we can right-click on the curve to animate the slider, and the point will then move along the curve. All right, so that's a nice little feature. It's not that complicated to produce, but it's very, very useful to show things moving along curves. Now, one of the nice little features about a cycloid, what exactly is it? The cycloid is the path which is traced out by a ball as it rolls along the x-axis. Now again, this is a little feature that I've drawn up before, and early in the 1600s, a lot of people were fascinated by these parametric curves. There was a French guy, Marin Mersenne, in 1623. All of these famous mathematicians of the time used to send each other letters. and they'd solve problems and send each other problems to be solved. So there's a little picture of Raymond Rosen, probably more famous for his work with prime numbers, but he, along with Tortorelli, Fermat, Descartes, and many other famous mathematicians at the time, were very interested in these sort of curves. You imagine how they would have had if they actually had a TI-Nspire to help them out, or even the internet, so that they could get responses rather than getting letters sent back and forward, taking a very long time. Yeah, so how smart were they without TI-Nspire, and we're using TI-Nspire to do all this? Well, one final property of this cycloid curve is this is basically the cycloid curve just with a plus sign there, so it's inverted. The cycloid curve has the property that if we were to roll a ball from the point A or the point A dashed, it would reach the bottom here, the point B, at the same time. People used to think that it would be a straight line, but it's not. It's actually the equation of a cycloid that gives that particular curve for the ball to reach that point at the same time. And these are the breakstone or sort of other curves as well. All right, I'm a bit sort of fascinated by some of these parametric equations as well, and some of these are just created in a very similar way. I'll just show you some of these other ones that I've created. These are a cardioid. So once again, we could do a geometry trace and see that the ball, the black circle is rolling around the blue circle, and the point traced out by the diameter on the circumference of the circle is what's called a cardioid. And we can also have sort of other famous curves here. If I change that value of k, I'll give you all these files and you can have a look at how this is done. But basically they're just the equations of the outer curve, and this is how I showed you before how it actually works and moves along the curve. Now we've got a cardioid. So this is when the point moves along the outside. So these are all basically called epicycloids, the ball moving or the circle moving on the outside. Similar ones we can actually have as the hypocycloid, when the ball is moving along the inside of a larger circle as well. And in these cases we get some what's called deltoids, or if I change some of these values from k equals 4, we'll get what's called the asteroid of this curve. Now it's asteroid, not asteroid, by the way there. But again, these are very nice little demonstrations. And once you know the secret that I showed you before, it's not that difficult to create some of these graphs. They are really illusions. It's not really the ball rolling or the circle rolling on the other circle. It's really just the center of the circle moving on a circle, and the screen is just updating all the time, creating that illusion. And that point, the red point, is actually just moving along the parametric equation that I showed you before. All right, so I'll just quickly show you one other thing that I've got today, which is a bit about projectile motion, which really, again, is just an application of the notes pages that we've got before. So if we've got a cricket ball being struck from level ground at initial speed of, say, 20 meters per second at an angle of 30 degrees, find the time of flight, the range, the greatest height, and the equation of the path. Once again, these can just be done on a notes page. So I'll just quickly show you what I've got here. The speed of projection, the angle of projection, we've defined the parametric equations, x1, x is vt cos alpha, y is vt sine alpha minus 1/2 gt squared. A formula for the time of flight, which we can get from all the textbooks, 2v sine alpha on g, and we've defined g to be 9.8 somewhere. Yep, g is 9.8. If we didn't do that, we'd get our answer in terms of g. The range, I've called this one Rx, is v squared sine 2 alpha on g, the maximum height reached, and the equation of the path. Now, the equation of the path I've also defined as a relational operator. Now, one of the nice things about this relational operator is that I can actually restrict the domain on that as well. So because Rx was the value for which it finishes, we really didn't want to see this graph going underground. So by doing this on a relational graph, restricting the domain, given that 0 is less than x is less than Rx, we'll only see the projectile moving. And once again, I've done a similar thing to what we've done before, so that we can animate this graph and see the graph moving along. So once again, if you were to use this in exam situations, which is often multiple choice type questions, where all you really want to do is to find the value of the maximum height reached, or to find the range on the horizontal plane, or to find the maximum height reached. So one other quick little question, which is very similar, but this time when it's not thrown from the level. So this time it's actually thrown from a cliff 2 metres high. Basically, it's exactly the same. The only difference here, we add in the plus h in the relation, and we also add in the plus h in the y value. But then to find the time of flight, we have to solve when y1 is equal to 0. And we get the graph of that as well. So we can see that it's being thrown from an initial height of 2 metres above the ground. Window settings would obviously have to be changed for different values of v and alpha here. And one other thing, I think in these type of questions, we can actually find the speed at which this thing hits the ground. So I'll leave that. I think I've taken up enough time here. There's plenty of other things that I'm sure Chris will show. We can look at some variable acceleration problems and some dilution type problems, which again is another one with a salt solution. Once again, if you define all of these variables, the input, the output, you can use your notes page to just solve the differential equation here. So I'll let you look at that one in your own time and hopefully pass over to Chris, who'll show us some more interesting activities.
Thank you very much, Ray. So while Chris is getting set up, that was fantastic, and I think that you've really highlighted the power of that notes page in terms of students being able to use it in so many different situations. And yeah, the nice thing about technology like that as well.
Yes, that's what I said. These famous mathematicians, how would they have been in the 1600s if they had TI-Nspire? I think it's quite amazing that they were actually doing this sort of stuff without it. You know, and here we are trying to do it with it.
Well, also you're just thinking, oh, you know, you take one of your files and just go, oh, I'll just try that. And that's the nice thing about technology and with students is that you show them the starting point of it, and it's amazing where they'll go with something like that, isn't it?
Yeah, and those things look sort of pretty complicated the first time I created them. I thought, how am I going to do this? But they're not that complicated to do once you know the little secrets that I hopefully showed you, and you can have a look at these files yourself and look at them. Anyway, I better get over to Chris.
Yep. So Chris, it's all yours. Thank you, Ray. Chris, you can see your screen. It's all yours, my friend.
Okay, thank you. Good evening, everyone. So I'm just going to talk about really how a student could prepare their CAS calculator before they actually walk into the exam so they could solve questions faster. And at my school, we use quite a few of these things that's up there. User-defined functions is one that most of our students do use on some form. Some are complicated, some are quite easy to do. Notes pages, Ray was just talking about that, so thanks for a great presentation there, Ray. Widgets is something that's a little bit new. If you'd watched the math methods exam Readiness, you would have saw Craig show a little bit about that. Programming functions, if we get time, we can have a look at that. And really, a student really needs to know how to use the menus and all that on their CAS calculator and know how to find them quickly before they walk into the exam so they're not wasting precious seconds. Just for user-defined functions, what I like to do is I like to get students to solve this simple vector resolute question. Well, we might say it's simple, but by hand it will take quite a while to do, and even with a CAS calculator, once they work out the magnitudes and all that, it still takes quite a while to do by pressing the buttons in. So if we actually have a function set up on the CAS calculator before, if we see this one here, basically all I've done is set up the function beforehand, and the students will just type in the coefficients of the two vectors and then press the answer, and this is our I, this is our J, and this is our K component. Just before we get in to look at the actual CAS TNS file, they could do it with a notes page, which is inside a file, and it's all pre-set up so that all they do is at the top of the page enter in the values and then scroll down to where the information is. The third slide there was from widgets, and I'll show you how to import some widgets a little bit later. But the only difference between our notes page and our widgets page is that when we import the widget, all of the formulas are deactivated, and we have to go inside that and activate all the Mathbox formulas. So that can be a little bit annoying. It'd be interesting to know how many people have actually tried to use user-defined functions in the chat window or widgets already. So if we get into this first one, I've got some functions already set up there, but basically what we've done here is I've pre-set up some user-defined functions on the CAS calculator already, and if I press the var key, I can scroll down to see what's there, and basically all I do is select the formula, and reading off the question which is on the previous sheet, slide that was there, we could just type in the values, and I'd say that if someone did this by hand, it might take them 1.5 to 2 minutes. If they did it with a bit of CAS at the same time, and I'm talking, so I'm doing it rather slowly to put in the numbers, and as soon as I press enter, I get the answer. And if you're really on the ball, you could probably do that in less than 20 seconds on your CAS calculator. Students at my school, they will use this one, and when I first do this, as I said on the slide, that if I get them to try this question by hand, it'll take them a while, and then say, well, now use your CAS, and then as soon as I bring up the user-defined function and just type the 6 values in and press enter, they're quite amazed at what the answers come up as and how quickly it is, and I normally get a wow that's there. So they really enjoy that one. And the whole purpose of my little session tonight is to try to show how we can set up the CAS calculator with our students quite easily and quickly to save them those precious moments in the CAS Active exam 2. And if they can save 30 seconds to a minute on that question that we just did or a similar fashion, then we've taken a little bit of pressure off and they've got more time for other sections of the exam. So that's the question that was there that we just did. And this is just the notes page, which is in the same file that we have there. We just go into as Ray was showing, we just go in there and change the values. Sorry about that. We could get the values, and if we update the values, everything down below will automatically update. So that's a good thing to do. And if we have a look here, if I change the value here to a 5, everything automatically updates. And this is as if we'd pulled it in from a widget, as we know, and I'll show you how to do that in a moment. All the formulas are turned off. So for a widget, I would have to insert it, and I go to widgets and scroll down to where it is. This is under vectors. Just press add and it comes in. Scroll up to the top and we have to go inside all the functions to activate them. And once they're activated, and for that question, we'll have to scroll down to see where the appropriate one is, which will be this one. We have to go inside the actual math box, press enter. That's our scalar resolute. Keep going down until we find our vector resolute, A parallel to B. Press that in, and we've got some answers. And we've got all these other formulas that are there, so students can, as they come up with the appropriate question, just highlight the one that they want and press enter, and they'll get their answers. So they're very easy to do. The only one thing, if you have tried these on a handheld, in which as teachers we should try this, using the button here when we bring up our mouse, and it's very hard to show on the computer itself, but as they move around the screen to try and enter these values there as they change, it's quite hard on the handheld, especially if we've got to go through and scroll through these down to the ones that they actually want. So that's one consideration we need to have. I guess at this stage, if we could say something to the programmers at TI, if it was possible when we actually import the widget into the file that all these math boxes could be activated immediately, and it would save a lot of this playing around with the touchpad there and using our finger to go down to the appropriate math box that we have to activate. So that's an annoying thing. So if I said of my favorite for these formulas, I would say this would be the quickest to do out of all three. The notes pages and the widgets are really good because if we've got a weaker student, they do put some explanation in for the students there, so it would help them. Over here, the student needs to know a little bit more about what's going on with which formula they need to apply, because there's a little bit of shortcut there. I suggest that when they actually make the names to these, there's something which is useful. As you can see, it's vector resolute perpendicular is the code I've used there. When they actually do make up their own rules, I suggest they have more than one letter, because quite often we may delete variables and anything with one letter is going to disappear. So if we call it more than one letter, it won't get overwritten if we're going to define another function which we've just called that letter. Like we might have something F for something, and then quite often in the exam they've got formulas that, or rules that we type in which are fx equals, and that will just overwrite the rule. So 2 or more letters are appropriate for that. A question where it could be useful for is also with some force questions, and again we've got our question here: a particle of mass 2 kilograms is acted on by a force whose magnitude is 2t minus t squared units, where t is time in seconds. Find the velocity of the particle at the end of 5 seconds if it has an initial velocity of 4 meters per second in the direction of the force. So we see by hand it would take a while to do, and some students would do that even in the CAS active exam. What we can do is we could use the differential equation solver that's there, the inbuilt function. We could use a more sophisticated sort of formula that some students would do, rather than on the first version they've worked out the equation and then they're substituting the value. We're solving an equation this time with t equals 5 that's there, giving the answers there. Or what we could do is set up a definite integral which will also solve it. And as I say there, all of these methods take quite a lot of time to type into your CAS on the spot, and we all know that students are quite slow at that. Is it possible for us, or can we reduce the number of keys pressed? And if so, that would save a lot of time. So what I prefer to use is what's known as a user-defined function. Some people will call them macros, and on a calculator page that is here. And as you see, I enter in the function. It's in W at the moment, and we'll come into when we have a look more closely at it. And I've worked out the value with just typing in this, and I don't have to go up to the top terminal as the integral, press arrows down to the bottom terminal, etc., move to the end. I just have to enter my values inside this user-defined function, or UDF, that's there. If I change the last value 5 to an actual t, the variable in the derivative, I can actually get the equation that we saw on the last page back here. So there was our equation that we see with that. How are user-defined functions set up? Well, first you come up with your idea that's there, and in the specialist course this rule is quite often put in where we have to make an approximation of a rule that we cannot, or function or relation that we cannot actually integrate, so we put it in and we do it this way. So there's 2 ways on your calculator page that you could actually do this. You could use the define key and put it in, and we've got R is our rule. Now Don't worry too much about these explanations. I'll show you a file shortly with all the ones that I've set up for tonight's session. You can have time to play with at a later stage, pass them on to your students, and we've got that. Otherwise, you can use the assign key, which just means it looks a little bit neater as you go. So just to talk about our rule that we have here. So they're really just predefined shortcuts on the CAS calculator to save time pressing buttons that we put on our CAS before the exam. So I've got an explanation of what's going here for you, and there's our two screenshots from before. Now, there's a TNS file that will be available to you that will have all of these functions listed in there. I've done the vectors, and you'll notice that I've actually used by hand method calculation, because when I first did this about 4 years ago with some students, they said, we've got no idea how to use the inbuilt functions on the CAS. So I said, oh, well, let's just do them by hand, how we do it if we were going tech-free. And we just built up the functions here and stored them on the CAS. And what you'll find is there's the rules that I was showing you before. I've got an example of how they're all used that you can go through at your leisure and have a look at. It's in there, scalar, resolute, perpendicular, etc. And there's examples of all those. I've got some miscellaneous formulas also included in here, how to find a stationary point of a graph, and we just put the rule in there, press enter, and it gives us the stationary points, and sometimes we'll have to scroll across to see the second one. It works for trig functions, providing that you do your domain included there. There's some Cartesian form to polar form, and pole to Cartesian, and asymptotes, hyperbolas, and then it goes on, and there's even one on the next page about a double integral that you might use in some of the specialist questions there. So, these are all the functions that are listed that we were just talking about. You will have the TNS file available for you. It is here. And there's some instructions in there for you to see. If I press the var key, all my functions are listed here that we've got. And moving along, there's the examples of all the problems in that worksheet where you can go and have a look about how to do those. And they're very quick and easy to do. Now, it is quite possible in a calculator page we have some issues, and I'll have to, because of time, I'll just have to let you read this. But what we've got in the calculator page, if I add a new problem, see I've got my vars here, there's all my variables defined. If I actually add a new problem, if I actually insert a new problem, what we find, and just to calculate, when I press var, these no longer are there. What we could do if we really wanted to, we could use the page sorter and scroll up, and we can actually copy the whole thing, Control C and Control V, and paste it, and what it does, it will then set up the pages where they're all fully functional. So we've just copied everything and they're all fully live in the next problem. And that's quite a useful thing that you can do at times. So I'll leave you some reading there. All the notes and that are in the TNS file. It is quite possible to set up all of these through a library shortcut so that we can do them from elsewhere. and we can also set them up as functions. And with a function, what we can do is we can actually list some instructions for the student. From my experience, this is not that useful, because what you would get is you get the student in their bound reference, put a list of all the rules that they have into that, and they can just refer to their bound reference to see what the functions do and what to put as the input. Now I'm just looking at the time there, so I'm just going to scroll down to a couple of problems that we've got here. Now some VCAR style questions, and these are similar to last year. So I've looked at last year's exam paper, and I've just picked some questions that would be useful for us to use these user-defined functions already inbuilt into the calculator. So I've chosen this one, and I've put the multiple choice answers. In reading time, a student could already decide what function they're going to use. This is our one, which is Cartesian to polar. They just type in the two numbers here, press enter, and it gives us the answer, and they've just got to be careful with a minus there to realise which value they're going to pick. This is another question where we've got our first vector here, for W in there, we've got our second vector here, and where W is a real constant. If the scalar resolute of A is in the direction of V is 14 over the square root of 29, then W equals. What we can do is we can actually put our user-defined function in here, and we can use the solve function at the same time to work out what the value of W. The notes page, which we have this, unfortunately I found no easy way, unless I know what the question's going to be, to actually solve that in one step. It's almost impossible. I've tried. Again, this was another question. We've got the vector A and the vector B with an unknown n in there, and we've got to add the two vectors together and work out what the value of n to make them perpendicular. So the student would realise we've got to use the dot product, and again all I'm doing is working out A plus B, and then putting in those values, the first three, and then we're putting in our vector B with the next three values, putting it inside a solve function, and it will give us the two answers there that are possible, and we just go to the multiple choice answers. I've eliminated the possible alternatives there just to show you how it can be done, and that's almost identical to a question on last year's exam, so I'm sure that would have saved a little bit of time there. Another question that was on the exam, we had a random sample of 120 apples from a given area, has a mean of 250 grams and a standard deviation of 18 grams. Assuming the standard deviation obtained from the sample is sufficiently accurate estimate of the population standard, an approximate 95% confidence interval for the mean mass of apples produced in the locality is given by this. So this time what I did was I set up a notes page. I imported it as a widget, as you'll notice here, because they're not live formulas, as I showed you before how to do that. And then I've just gone down to where the appropriate 95% confidence interval, highlighted over the math box, pressed enter, and then gone to the next math box and pressed enter. So for a weaker student, that may be a good way that they can get these answers. And the next question you have, and what we have to do is, this is now one of the inbuilt functions on the CAS calculator, and a student has to know. So we've got lifetime of a certain brand of AAA batteries is normally distributed with mean life of 22 hours and standard deviation of 1.5 hours. A random sample of 20 AAA batteries is selected. The probability that the mean lifetime of this sample is 20 batteries exceeds 21.2 hours. The student just knows where to put it in, and in the appropriate template puts in the values, and we get our answer, and that would agree with one of the alternatives of the multiple choice. So they were all multiple choice questions. And again, we've got another one about sampling. Now this question had quite a bit of debate about in the exam, because it wasn't what a lot of students expected as the answer. So the main thing in the question was that it says that we have apples grown on this farm, 184 grams, and standard average given. And the key word here is independent. These are all independent. So rather than have an A squared there and a B squared there, we have to take A and B. because it says the questions are independent. And again, I've set up a notes page that's there for this, and putting in the information, the 6 values could be quite difficult. And again, I would probably be importing it from a widget that's there, and I have to activate all the math boxes. And we can see we had to calculate the mean and the standard deviation. So be very careful with that one that's there. The last question that we have is about some hypothesis testing, and again it's similar to part of the questions in part 2 of the exam. So we've got this supermarket chain showing records of a popular shopping item, has an average monthly expenditure per person of $12 with a standard deviation of $1.60. Running the sales campaign, they would like to know if the sales have improved. They sampled 30 families and found their average monthly expenditure per person of $12.50. We are to test this at the 5% level. Now, again, this time I chose to do it on a calculator screen, as a lot of students would do, and we've put in our test statistic that's there, put the values in, but before that we had to always say that H0, nothing has changed. So we assumed that nothing has changed to the population mean. We then are told we want to know whether it will make it more popular for the shopping item, so we're going to have it greater than 12. We will calculate our test statistic from the values, and then at the 5% level we have to work out what we're going to compare it to, and from the calculation we see that our test statistic was 1.71, and at the 5% level of significance we reject H0, the null hypothesis instead was greater than 1.64, which we then would have to make a statement and make sure that students clearly state H0 is rejected at the 5% level of significance. Just the last thing that I'd like to mention, as I see the time's gone, students need to know about their calculator, and some students may use some of these. A lot of students will use the notes page or widgets or whatever. Programming functions, for me personally, I wouldn't do a lot of that. I don't see a great advantage since we've got our bound reference. Students need to know all about their inbuilt CAD functions that are there and know where to find them and use them quickly. The other thing that some students do is programming. And again, I don't see a great advantage to that, but the biggest advantage I see is this user-defined functions. I know it's been a short amount of time that we've had to go over this, so when you're doing your, you're going to have a survey to fill out. If you'd like to see more about setting up user-defined functions, please mention that in the survey, and I would say that it is a useful thing to do with these user-defined functions, and the students at my school will find them very useful for certain topics. And as I said, I started to use them with the vector resolutes perpendicular. That was the first thing, and then we just added as time has gone by. So if we can save 30 seconds on one question, 70 on another, whatever it is, I think students then feel a bit more relaxed and they've got more time to look at those harder exam 2 extended response questions. So John, that's about all for me, and I'll just say pass it back to you.
And thank you very much. Yeah, you say that's all from me. I'm blown away with what I've seen tonight by both of you. So thank you very much, and fantastic that we've got these resources that we can watch again on demand, and that you're willing to share, both yourself and Ray, those resources with all of us. So thank you both of you, Chris and Ray. That was absolutely amazing, and some really nice feedback from the people watching tonight. So thank you for those comments too. So as we do begin to wrap things up, if you do have any last-minute questions, please try and get those answered, as I know Chris and Ray will endeavour to answer them. Or equally, we will add those to planning of future webinars, as Chris mentioned. So when you do leave tonight, the webinar will take you to a brief survey, which will automatically appear here in your browser. And your feedback does guide us as we plan future online events. We do listen to your feedback, and so we do hope you share your thoughts in a post-webinar survey. Importantly, your certificate of attendance will be emailed to you in the next 48 hours, along with a link to our on-demand and YouTube versions of the recording, as well as the relevant documents that both Chris and Ray mentioned earlier. After we leave tonight, if you need some post-webinar follow-up, feel free to phone or email us, as we would love to hear from you, and there'll always be somebody on the Australian team that will be willing to talk to you and help you out and direct you to the relevant person that you may have any questions about. And sadly, that brings us to the end of tonight's webinar. Thank you so much, Chris and Ray, for everything that you have shared with us tonight, and the participants. I know we all really appreciate it, so thank you.
Thank you.
Good evening, everyone. Thank you.
All the best. Bye.
Bye.
And likewise, we do this for you, the people who are watching, so thank you for joining us, and we hope to see you back online again soon. So have a great evening, and good night.
Bye.
Good night.